Hi, Electron John from AST here, and today I promise to show even the most advanced scope users something that I know that they have probably never done with the lab scope. So we're continuing on from a previous video we did where we talked about using some pressure transducers and diagnosing different stuff on a car. But with that being said, the whole theory behind computer controls is all about sense and adjust. And what that basically means is every time that the oxygen sensor senses a lean condition, its response is to go ahead and richen up the fuel mixture. Every time it senses a rich condition, its response is to do the opposite. It needs to do that so the catalytic converter can do its job properly. So a catalytic converter basically is there to clean up three different types of poisonous gases. CO, if we add some oxygen to CO, we turn it into CO2. If we add some oxygen to HC, hydrocarbons, we turn that into H2O, which probably explains why you see water coming out of the tailpipe when you're at a traffic light on the car in front of you. And then we also have NOx. So that's why we need to switch between rich and lean mixtures, because we need the mixtures to be lean at times so we can store oxygen, so we could clean up HC and CO. But we also have the rhodium inside of a catalytic converter, which needs to be there to help clean up NOx. Now, oxides of nitrogen, that's another poisonous gas. Most of the time we're going to try to attack those pre-combustion as opposed to post-combustion. But anytime we're dealing with an oxygen sensor waveform, and again, you could always go to generic OBD2 to see actual O2 sensor voltages. So I know a lot of times we're dealing with lean air fuel ratio sensors now, if we were on the factory side using our scan tool. But on the screen you guys see that's a typical oxygen sensor waveform switching from rich to lean. And anytime we have a higher amplitude on that waveform, that's representing it's reading a rich condition in the exhaust. Anytime we have a lower part of that amplitude there, that's representing that it's a leaner exhaust. And we also have the catalyst sensor. So we, in OBD2, in order to set a P0420 or 430 code, in essence what we're doing is we're comparing the amplitude and the frequency of the pre-cat and post-cat O2 sensor waveforms to see, as long as they're not 30%, as long as the post-cat is not 30% or more of the pre-cat O2 sensor, we won't set a 420 or 430 type of trouble code. So you might want to say to yourself, well, how do I know possibly if the catalytic converter is good or failing? And there's a million different ways to do that. We'll talk about not all of those today. I'm just going to give you one quick little thing that we can talk about as far as catalytic converters go. But throughout future YouTube videos, we'll talk and explore and show you guys how we can go ahead and test catalytic converters 100 different ways. But for sake of today's YouTube video, we're going to just talk about going ahead and driving the vehicle here. So we're going to go under a heavy acceleration in low gear, and then we're going to go into power enrichment. So under those conditions, obviously we need to add a whole bunch of more fuel to the mixture, and both front O2 sensors should go rich as a result of that. Then we're going to go ahead and decell the vehicle. When we decell the vehicle, we should see the storage capability of that oxygen, of that catalytic converter. So we should see that. We can just do a little quick countdown in our head, and we can see under those times, under decel and leanment, we can see how much oxygen can be stored in there. And that's a quick, easy way. We don't need a scan tool. We don't need the actual scopes. We don't need a whole bunch of fancy tools that we'll talk about in future YouTube videos. But that's one quick old-timers way to test it. And remember from the last YouTube video that there's a lot of things we can do with those oxygen sensor PIDs to help me determine if I have a fuel system problem or an ignition system misfire type of problem. Let's talk quickly about some computer control facts. A big thing to remember about any computer, car computers, house computers, whatever, is they only think digitally. So binary coding, zeros and ones, something's on or it's off, right? They cannot understand any type of analytical type of input, which you know that there's a ton of analytical sensors on a vehicle. Stuff along the lines of a throttle position or pedal position sensor, temperature sensors, whatever. So this is something important for us to understand, because that means that all of those signals, if they're being created, somewhere there has to be an analog to digital converter to convert that to something that a car's computer can understand. It has to convert it to digitally. So we have the RAM and the ROM and the PROM, just like we would on any type of computer. That's all different types of memories. But for the most part, keep in mind that no matter what the component is, if it's not creating in its natural habitat a digital on-off type of waveform, so like a square wave, it has to have an analog to digital converter to convert that to a digital signal. So with that being said, we have some other computer control facts, and they are that the computers are all going to talk at different baud rates, so there's many computers on the vehicle. This is all done through the networking. That's going to be another future YouTube video as well. And then we also have some universal PCM strategies, and this is something in my intro classes I always try to get across to all the attendees. That, for instance, we all heard of, open closed loop or limp mode. Those are two very popular ones. Clear flood mode, that's another popular one. But we have startup mode, we have different modes of operation. And we'll use for an example the startup mode. In startup mode, let's say the customer brings you a vehicle and they say, hey, this thing's hard starting or it has poor performance as soon as I start it up. But as the vehicle warms up, it's fine, the problem goes away. If your standard routine thing is to pull the car in, hook a scan tool up, and pull out trouble codes, and let's say in that scenario you pulled out an oxygen sensor trouble code, well, that might be a problem, but that's not going to fix that guy's complaint, which is going to make us look bad in the industry by not fixing what the vehicle was brought to us for. You can kind of see that under those conditions, in startup mode, let's say, we're looking at basically the RPM sensor, we're looking at some temperature inputs, we're looking at the throttle position sensor. We're not even looking at the oxygen sensor. Some vehicles will also look at the NOx sensor under startup mode, because while we're starting a car, that's a very noisy time. We got a starter motor engaging into some teeth on a flywheel or flex plate, however the car is engineered there. It's a very noisy time, so we don't want that extra ignition timing advance. So the NOx sensor does its job. It tells it, hey, I know I'm in startup mode, I know I'm cranking because the RPM is relatively low. It's only as fast as the starter can turn the actual crankshaft over. Plus there's a lot of noise going on during that. So keep in mind, this is a point I always tell to some of my intro level students that come to my classes here, that always understand the different modes of operation and compare it with what the vehicle was brought to your shop for. It's not always just going to look at trouble codes and then trying to attack those codes, because the number one thing to keep customers satisfied is to go ahead and address the problem why they brought you the vehicle. So let's continue on here. Some of the stuff we're going to be talking about is going to be important for us to understand as kind of like a baselining here for the different types of tests we're about to do here. We have two different types of load sensors found on a car. We have a MAP sensor and we have a mass airflow sensor. It's important for us to understand the difference between them. So if it's a MAP sensor, it's going to be hooked up to an actual vacuum hose of some sort. Anytime I open up the throttle plate, so anytime there's a load on the engine, I'm stepping on the gas pedal, and I take away that mechanical restriction, vacuum's going to drop. When it sees that the vacuum has dropped, it assumes it's under a load. You're stepping on the gas pedal, so at that point, it wants to add more fuel to the mixture so that we can actually, accelerate the car, climb up the hill, whatever the case happens to be. We also have a mass airflow sensor. Now, a mass airflow sensor operates a little bit differently. Here, we're not measuring vacuum, we're measuring the total volume of air that's coming in the engine. And to do that, there's a lot of components in a mass airflow sensor, but the one that we're going to talk about here is that hot wire, right? So the hot wire on your screen is the one on the bottom, and it's black in color. We're going to talk about that here in a second. We'll heat that up to about 400 degrees Fahrenheit as we step on the gas pedal and more air is rushing past that hot wire. It's measuring the whole volume of air entering that engine. Remember, the engine's nothing more than a big air pump. So now we can determine basically how much load is being placed on the engine by the volume of air that's passing that hot wire. Now that hot wire, as you all know, the experienced guys in here all know that if I take a piece of metal and I heat it up and cool it off enough times, it starts to get insulated, right? So it starts to turn dirty and black and carbon. Some cheap air filters will also start coming apart. Maybe there's a rodent's nest or whatever that got past the air filter. Anything that's covering that hot wire is acting like a layer of insulation. So what that means is if you go outside on a cold winter day and you got, your whole snow parka suit on, you'll eventually feel the cold air, but it's going to take time because you're insulated. Same thing happens when that hot wire gets insulated. Under those conditions, what ends up happening is you step on the gas pedal, there's a lag before the computer even senses that incoming air past it. So you'll get some tip-in hesitations, maybe even stalling out, a backfire, something like that, until it catches up to that incoming air. So we want to make sure that hot wire is not restricted in any way. We're going to talk about how to do that here in a second without having to take it out and physically look at that hot wire there. So those are two big differences. Now, if I happen to have a vacuum leak on a mass airflow sensor or some pirate air, unmetered air entering the engine, the exact opposite happens. It does not understand that there's extra load being placed on the engine because I'm getting some unmetered air that's never going past that hot wire. So there's a big difference between speed density and volumetric. So volumetric being mass airflow, speed density being MAP sensors. All right, so we kind of talked about the differences between them. The next thing I kind of want to pull up is always when you're approaching a diagnostic dilemma, whatever it happens to be, is to try to think the way how the computer is geared to operate. Then you have a much better shot at being able to diagnose a car. Now that's assuming that you had the proper training over the years and you understand how a computer is supposed to operate. So, going back to richening the mixture and leaning out the mixture, there's something that's called fuel trim. And we addressed this as one of my 6 main go-to PIDs in the earlier YouTube video. But fuel trim started off with integrator and block learn on General Motors. I'm not going to talk a whole lot about that, but integrator was basically short-term fuel corrections. Block learn was basically long-term fuel corrections. And nowadays, 0% is our target. 0 means, hey, it's perfect. That I got just the right amount of fuel mixture going into the engine, right? If I sense that I had to go ahead and add fuel because the exhaust oxygen sensor is running lean, my numbers are going to go positive. If I sense that I had to do the opposite of subtracting fuel because the exhaust content is rich, the numbers are going to go negative. We would love it in a perfect world to be 0, but in all reality, we have short-term and long-term. Short-term are small corrections that eventually are going to get kicked back down as long-term changes. Long-term are longer-term corrections, right? So here's what I tell people. I use short-term fuel trim diagnostics to help me diagnose any type of vacuum leak, something at an idle type of problem. I use my long-term fuel trim corrections for the whole dynamic response. So am I adding fuel while I'm accelerating? Am I adding fuel the entire time the car is running? All that's going to mean something different as to what I want to focus my diagnostic attention on. If it's constantly lean and I'm constantly adding fuel, I'm going to be looking for something like a weak fuel pump or a restricted fuel filter, stuff along those lines. That's my analytical brain that we just talked about, understanding how a fuel system is supposed to work. So now, as we keep going on here, we have our oxygen sensor that we talked about. Remember, the big thing we wanted to make reference to on that is, I know that on the OEM side of a lot of today's cars, there's not going to be an O2 sensor reading like you maybe are accustomed to seeing. But again, if you go to the global side, you will definitely still have that 0 to 1 volt O2 sensor reading that you can actually go ahead and use in your diagnostic routine. Going through with misfires, this is another thing I wanted to kind of take into account here and share with everybody. The way the misfire monitor works is we're measuring how fast that crankshaft's spinning. If there's a misfire that occurs for any reason, say a spark plug's bad, I don't care, you make up whatever reason you want. It's going to slow that crankshaft down because we don't have the combustion forcing that piston back down inside there. So it's going to momentarily slow that crankshaft down. It always uses a backup. In the previous YouTube video, I said always back up your suspicions. Computers are no different. If in fact that crankshaft did slow down, and in fact there was a misfire, remember, just the act of combustions, if the air-fuel mixture did not ignite inside that cylinder, that extra oxygen was never used up through the act of combustion. So it's going to, the oxygen sensor, right after the crankshaft slows down, I should have a whole big puff, entire cylinder's worth of puff of oxygen content. So that mixture should go lean on that particular O2 sensor. So if it's a 4-cylinder, it's only going to be the pre-cat one. If it's a V-design engine, you're going to have 2 pre-cat O2 sensors. So whichever side of the engine had the misfire present on. So you saw the little waveform how that looks in real life when a misfire is actually captured. Then, as we continue to go on here, there's 2 very popular types of sensors that we're dealing with as mechanics. One is going to be a 2-wire sensor, one's going to be a 3-wire sensor. Occasionally we'll have more wires going to it, but a lot of times, you know, those are just some extra circuits there. So it's real easy anytime I'm dealing with the 3-wire sensor, because most of the time on a 3-wire sensor, you're going to have a signal voltage, so a 5-volt reference most of the time. You're going to have a signal ground, and you're also going to have the signal return wire. So what that means is the computer is giving that sensor 5-volt reference. We'll use that numeric value as an example here. There's also going to be a ground wire that's being supplied from the PCM down to that sensor. And then there's going to be the wire that goes from the sensor back to the computer that's telling it the difference. So in the case that we just showed there with the map sensor, you know, depending on what that vacuum is reading, it's going to change that 5 volts to a lower voltage on that particular sensor. And that's how the computer can look at its lookup tables and determine how much load is being placed on the engine. So a lot of times we pull out a trouble code, comes down to 3 possibilities. I could have a bad PCM, a bad sensor, or a bad harness going from the PCM to the sensor. So a real quick way you can do this is you can unplug that sensor and you can jumper the 5-volt reference coming from the one terminal that's coming from the PCM back to the signal return wire. Look at your scan tool screen, you should see 5 volts, right? If you did, you ruled out that the 5-volt reference is good. You also ruled out that the harness going from the computer supplying the 5 volts to the sensor is good, and the harness going back to the computer from that sensor is good. Also, I can then go ahead and take a digital voltometer and just touch the 5-volt reference with my red lead, take my black lead and touch the ground one. If I have 5 volts, I just ruled out that the ground is good as well. Plus, you know that the computer is good. So at that point, assuming there's not a vacuum leak in that one example there, at that point, probably going to be a bad sensor, right? Now, here's the little tidbit that I have never heard of anybody else in the industry with the exception of one other instructor, the guy that I learned it from, and I'll give him props. Many, many years ago, a good friend of mine named Ron Ballou actually taught me this. I want to say it was in the early 90s. But how can you test an analog to digital converter on a vehicle? I don't ever hear about anybody talking about this. Anytime you want to do an analog to digital test, a lot of times here's the scenario. Let me pre-course it with this scenario. If you pull out multiple trouble codes on a car, and obviously you're probably not going to have that many faults with the car, right? And you happen to look at these trouble codes that you're pulling out, and the trouble codes are, you know, let's say it's a map sensor, not a Ford map sensor because that's a digital one, but let's say it's a map sensor on any other type of car, and let's say it's a temperature sensor, a whole bunch of temperature sensor stuff, throttle position sensor or pedal position, and you ask yourself, what do all these things have in common? Yeah, they might share a 5-volt reference, they may share the ground, but they could also, all of those are analytical style sensors, which means a computer has to convert them to a digital signal. So the analog to digital converter that's located inside the PCM could have failed, which is why, even though those sensors and circuits and everything may be working the way they're supposed to, computer can't understand any of the language that it's receiving from them because it can't convert it to a binary type of signal. So what you can do is you could take whatever sensor is easiest. So I used as an example there I unplugged the throttle position sensor, and I just went ahead and jumpered the 5-volt reference to the signal return wire. I took a scope and I just took the black lead of my scope, hooked it up to a ground, you know, it could be the engine block, whatever is easiest to hook up to. Take my red lead and connect it to that connection that I got where I've shorted the 5-volt reference and the signal return wire together. I should have a rock steady 5-volt line going across my screen under those situations. If that line appears to be bouncing up and down, then you've got a bad analog to digital converter, which is why you're setting all those different types of trouble codes that all have to do with something that's not a digital type of sensor. So again, I've only heard that talked about one time, never heard them repeated afterwards. I've done this test with a bad analog to digital converter, and it's a rock solid test. So even if you're a very experienced scope user, my hunch is you've never heard that test before, and remember, you heard it here now, and go ahead and use it. Use it in your training classes, use it in your diagnostics, whatever the case happens to be. So the two most popular requests that I always see people asking for help for in all the different automotive forums are anything to do with an ignition system pattern, and granted, you know, if you're not old like me, you probably didn't have to deal with those a whole lot. And then also cam crank waveforms, right? Does anybody have a known good cam crank waveform for whatever? That's going to be a future video. Let's talk about ignition. Secondary ignition pattern. I've got the firing line and I've got the spark line. Now, think of the firing line as the amount of energy it took to jump the spark plug gap. And think of the spark line as the amount of energy it's taking to keep that spark or fire, or whatever you want to call it, going across the gap. And they're in 100% relation to one another. So if I was to take the firing line and the spark line and lay them out, that should equal out whatever the coil output voltage happens to be. So let's just throw a number out there, 20,000 volts. So that means if it took me 18,000 of that available 20,000 volts to jump the gap, there's only 2,000 volts left to keep that fire going across the spark plug. So under those conditions, if you think about it like that, there's a wealth of information I can obtain by interpreting that firing and spark line. So on the next screen here, we've got some examples. If for some reason I have a lean condition inside that combustion chamber, that means there's enough fuel to start the fire, but we're running out of fire. We're running out of a fuel source, so it's becoming harder to keep that fire going. Now, the exact opposite holds true for a rich condition. If that line is sloping down, it's got a lot of extra fuel inside there. Could also mean some guys are going to be saying, hey, could be a weak combustion, right? So it could be weak compression inside of a combustion chamber. Well, on the far right-hand one, I showed you what that looks like. So this one is all cylinders on parade, but basically the far right waveform shows you what I call a belt loop. So we hardly ever have 0 PSI of compression. We might have, 30, 40 PSI. So there's enough that the waveform starts to look normal, but then we all of a sudden get this big belt loop drop to occur here. So think of looking at ignition patterns that way for secondary ignition. And you might say, hey, that's not very easy to do anymore on today's cars because of coil packs and everything else. There's all kinds of adapters. We showed you some of them in the preliminary YouTube video, so if you haven't seen that yet, definitely take and seek that video out. There's paddle probes that you can use. There's the inductive pickups. There's even a set of spark plug wires that you could take a whole coil pack off, put a spark plug wire on, put it back down. Then you can use your high tension lead and clamp right around it. So again, just get the right type of adapters that you need here. Now, if I'm looking at a fuel injector waveform, that's another popular thing here. Forever, we were looking at voltage patterns, and where it first drops down to where that spike occurred, assuming it's not a peak and hold style connector, but if it's a peak and hold from where it drops down to the second spike, whatever the case happens to be, that was called the on time of the injector. And technically, a lot of times we'd confuse that. We'd be hooking our scan tool up and we'd be looking at the millisecond pulse width, which it represents how long we're spraying fuel. And if I measured that part of the waveform and compared it to my spec on my scan tool, they never equaled out. They never equaled out because there's a whole bunch of fuel pressure holding that pintle shut. So it takes a little bit of current to ramp up before it actually has enough current to overcome that pressure holding that pintle shut. So then we have the pintle bump. So if you look at the amperage waveform, you saw where the pintle bump was hooked up at. That's when that fuel injector actually starts to spray fuel. Now, if I compared that time from where the pintle opened to the time that we shut that injector off, that matches 100% to your data stream on your actual scan tool. So again, there's another picture of the pintle hump, pintle opens, right? And we're just using an inductive current clamp to actually see that. Now, let's go ahead and let's get back to ignition, but this time let's talk about primary. And we're going to talk about primary because even if I can't easily see a secondary pattern, I can always see a primary pattern. So there's what's happening in the primary pattern. I'm going to point out a couple quick things. So right now, transistor turns on. That's when the voltage drops. That's if you're old like me and you had breaker points, that's when the primary circuit closed, right? Now we're charging the coil. We're charging the coil all the way until we turn the primary off. Notice that we also have something called a current limiting resistor on most coil packs. So here's what I like to tell people with this. If I take an empty pitcher of water and there's nothing in the pitcher and I take it over to my sink, I want to fill it up with water, right? So a coil pack is empty. I want to fill it up with electrons. Well, I don't go to the sink and just crack the spigot open. I let a whole bunch of water flow in there. Water pressure is real high, whole bunch of water is flowing in there all at once. But as it gets close to being filled, I cut the pressure down because I don't want to make a mess and have it overflow. Same thing's happening in that type of waveform. Right now, the coil pack is empty, so I got to fill it up with a whole bunch of electrons, but as it starts to get full, we're going to naturally limit the flow of electrons going into there, which is the current limiting resistor. So if I look at the amperage pattern, which is going to be a little bit easier on today's cars for you to actually use that as diagnostics, there's what the amperage pattern looks like, same exact problems. I'm going to show you that pattern live on this car behind me here in a second because there's two areas that are very important for diagnostics. Now you might be saying, hey, a lot of the V6 and V8 cars, I can't even get to the coil packs because there's an intake manifold. Well, remember, most of them are going to share the same power supply going to them. Computers controlling the ground on most vehicles. So go ahead and figure out, print out a schematic. You can use your amp clamp and you can see multiple cylinders, even if they are covered by an intake manifold all at once. Also, you can use your scope to do some fuel pump diagnostics there. So on the left-hand side of the screen is a picture of what a good fuel pump is. Now, this is not a three-phase fuel pump. That's for a future video. On the right-hand side of the screen is what a bad fuel pump waveform would look like. If you ever get a fuel pump that if the car gets towed into your shop, it doesn't start, or maybe a starter motor or a blower motor or whatever, but if you hit it with a hammer and all of a sudden it starts, well, or the fuel pump starts to turn on or whatever the motor happens to be, one of those little ramps would be going all the way down. That's going to be a short in one of the commutators. You can also go ahead and set your scope up for your advanced guys in here. Calculate the fuel pump speed. Fuel pump speed is going to tell you, between the speed and the amperage, is going to tell you if you have a restriction in the system, right? Also tell you if there's any gas in the gas tank. If I've got a mechanical restriction, the speed's going to slow down, the amperage is going to go up. If I'm not pumping any liquid, so there's no gas in the tank, well, the amperage is going to go way down, but the speed is going to want to go higher. Then at the very end of this, we had quick little silver bullets for diagnostics. Again, I'm not going to spend a whole lot of time because I want to show you some stuff here. I don't want to make this video too long, but we can use my 6 go-to PIDs to help me diagnose what exactly is wrong with this car. So at this point, when I get out of the driver's seat by using my scan tool and I open up the hood, I got some type of frame of thought of the types of tests I want to do. All right, so with that being said, I'm going to focus our attention now onto the lab scope over here. I'm going to show you a couple quick little things. So again, if you're a relatively new person, got a lot of comments in the last video that wanted to see deeper stuff on scopes, which is why I'm doing this in this part of the video here. So I'm going to just turn the scope on. We're just seeing some overhead noise right now, so that's because it's not hooked up to anything. I'm going to hook it up real quick too, so we can see a couple things here, to a little demo board, which I have different types of automotive signals on this demo board that I built. So I'm going to hook it up to an old-fashioned Ford map baro sensor over here, and I'm going to turn the power on, and the scope is in auto sampling. It's going to try to give me a picture. And whatever I hook it up to, it's going to try to give me a picture. Now, the Autel scope, along with most other scopes nowadays, it has a user-friendly, easy setup that you can do. I can go in there and I can hit the little car at the top. I could tell it I was testing a map sensor, and then it would give me a closer pattern than what I have right now. But the pattern appears to be walking across the screen. So what I can do, I just want to take this pattern and kind of show you a couple things here. Number one, since we're still in auto sampling, if I take it out of auto sampling, if I just go ahead and change a time base, time base, voltage scale, whatever, that will take it out of auto sampling. If I hooked vacuum up to it, making it work like a map sensor, well, technically you see what that does to the waveform. It appears to make it get a little bit wider, right? So if I take the vacuum away, I get more of those pulse widths on the screen again. So again, this is how I can use it to test some of the different sensors here. Now, I'm not going to take a whole lot of time talking about how to set up each one of these components on this video, but I'm going to take one more step on this easy sensor right here, talk about trigger. Right now, you kind of see that the pattern still appears to kind of be walking across the screen. If I turn the trigger on and I set a trigger level, now that pattern is still moving. However, it's locked on the screen. Now, the trigger and the zoom features of your scopes can really help you diagnose different parts of the circuits, which we're going to see when I hook over to this car. Another sensor that I kind of just want to show you real quick, and again, we're not going to be in auto sampling, right? Because at this point, I took it out of auto sampling and it was on the actual digital type of signal. So I'm going to go to an AC signal over here, and right now I got a knock sensor. Now again, the scope probably isn't going to want to display anything. I'm going to turn the trigger off. I always adjust the trigger once I acquire the signal. So a knock sensor, if you know anything about knock sensors, you know they respond to noise, right? So again, what I'm going to do is if I go through, right now we're in DC coupling, but I'm just doing this on purpose. So I know that knock sensor is going to create an AC type of pattern, but I want to show you what happens if I'm got it in DC coupling and I just tap on this. So even when I'm tapping on this right now, it will display a pattern. Now it's an AC type of pattern because once I took the trigger off, the scope reverted back to the auto sampling, right? So it went ahead and it knew what I was doing. That's not an actual live pattern right now, that's just the overall interference. But I'm going to go ahead again and tap on this. Nope, didn't hit freeze fast enough. And I froze the pattern on the screen. So anytime that there's noise on your engine, you would expect to see that type of pattern. Now, the louder the noise is, the taller and more frequency. So the amplitude and frequency is going to change out of that pattern. And again, that's why the manufacturers use that to help you, to help determine when it's in startup mode, the manufacturers that actually use that. Because that starter motor engaging some teeth on a flywheel, very noisy time. Now, what I want to do next is I'm going to go ahead and I'm going to hook up to a primary amperage pattern of a spark plug event. So I'm going to go ahead and I'm going to set my scope up before I actually do this because I have to tell it that I'm using a specific probe here. So I'm just using a low amp current probe. And I'm going to go into channel A. I'm going to go into probe settings. And I'm going to say, this is the one I'm going to be using. And we're going to say, yeah, I'm good with all that. I might have to come back to the screen and invert the pattern. Don't know, but I'm going to turn my unit on here and I'm going to zero out the probe. So it's running right now. I'm just going to hit this button and I'm going to start this car up and hopefully we're going to get a pattern. So got the pattern, it's upside down, right? So I can either take my probe off and flip it around, or remember, a good scope will have this feature built into it where I could just invert the pattern. Now, car's coming back down to more of an idle right now, right? So I'm going to do a couple things. I'm going to turn my trigger back on, because now that I got the waveform acquired, I can lock it on the screen. Now what I'm going to do is I'm going to stop the pattern, and I'm going to zoom in on a certain section here. Okay, so as you can see on the screen, when I first start ramping up that coil, there's a lot of resistance to electron flow. I always use this as an analogy in my training classes. If you're sound asleep at night and somebody comes busting in your bedroom and tells you, come on, let's go outside and dig a hole, you got a lot of resistance to working. Just like every single electrical component that's got a coil of wires around it. A lot of resistance to actually turning on. So I should see that up and down little hash marks where I first turn and ask this thing to start doing a job. If I don't see that, if I see a sharp uprise and then the slope, that's a pretty good indication that you've got a shorted ignition coil. So again, I went ahead and I just clamped around one of the coil feeds, the positive side of the coil feed there, and you could do positive or negative because current's the same on both sides of a circuit, right? That's basic electricity. It was easier for me to get to the positive side though. So I went ahead and clamped around that, and I was able to get a pretty good idea that there's nothing wrong with this coil pack just by looking at that type of the waveform. The other thing I want to point out is if it's a secondary problem, so that would be a primary problem. If it's a secondary problem, that's going to show up once you have the collapsing of that magnetic field. So the trailing edge, they call that, that's where you're going to see if it's a spark that's jumping outside of the cylinder, or a spark plug problem, a bad spark plug wire if it's got, still has spark plug wires. That part of the waveform is going to be where you're going to see a secondary problem. So you know where to focus your attention on. So again, I wanted to keep this video relatively short. I'm going to show you one last comment here, one last feature. And we have these extra little adapters from Pico. We have a red one and a green one, and obviously one tests ultrasonic, one tests frequency. So I can use these components here to test different parts of the car. All right, so I can actually use this particular one is measuring frequency. There's a lot of frequencies on cars. One of them happens to be this little button right here. So customer brings it in and says, hey, my door handle thing's not working properly. How can I tell? I don't have to take door panel off or anything else. I can just put this in close proximity, push a button, and I see that blip on the screen. And if I see that, whether it's that button or the push button start or whatever, I'm testing the proximity sensor to make sure that it works. So in your key fobs, technically in your TPMS sensors, they will have them as well. The other lead that's red in color works just the same, but it's actually used for testing like backup alerts and stuff along those lines. So again, if you like this video, make sure that you share it, make sure that you like it, give it the thumbs up, make sure you subscribe. Also, check us out on Facebook as well. So you can either go to Electron John on Facebook or my name, John Foro, on Facebook. You can also go to the website, which is www.electron-john.com. All that stuff will be in the comments below. Looking forward to seeing each and every one of you in our next video.